Hello, good evening. So today we are going to start a new topic, and probably next week we will do some more questions related to momentum, because I have seen the homework you have done and you have some mistakes. So we should go over these mistakes in our lessons next week. But today we will start a new topic. So the name of the topic for this week is going to be materials. So let's start from materials. So in this topic, so we will study springs and the mechanical properties of matter. So let's continue. So we will start from deformation. So what is deformation? Deformation of materials. Deformation means changing the shape of an object. So in order for an object to be deformed, a pair of equal and opposite forces must be applied to it. So by definition, whenever forces are applied to an object, the object is deformed. And we have some properties for deformation. Many deformations are not noticed, and many deformations spring back once the force is removed. So if there is no force acting on the matter, so the many deformations, many materials can go back to its original state. Now let's see in details. And we have two types of deformation. The first one is going to be elastic deformation. And elastic deformation means once the distorting force has been removed from a deformed object, the object springs back to its original form. And the most deformations are elastic. So when we remove the force from the object, from the material, and if the material goes back to its original position, so we call that one elastic deformation. And the second type of deformation is plastic deformations. And once the distorting force has been removed from a deformed object, the object remains permanently deformed. So it couldn't go back to its original state. And these kind of deformations are called plastic deformations. And the next one is going to be tensile and compressive forces. So the tensile forces means the equal and opposite forces causing extension in an object. So let's assume we have a piece of wire, and when we pull the wire from the both ends with equal and opposite forces, equal and opposite tensile forces, we may be able to stretch this wire. So these forces acting on the wire, equal and opposite forces, called as tensile forces. So the tension describes the pulling forces exerted by the wire towards its center. And if the forces acting on a wire are equal in opposite directions, like this, one is to the left, one is to the right, so these forces are called tensile forces. And the second type of force is compressive forces. The compressive forces equal and opposite forces causing, the same as the tensile, they were also equal and opposite. But for compressive, we compress the spring. Equal and opposite forces causing compression of an object. So two equal and opposite compressive forces squeezing a spring. And the directions are like this. And we call this kind of forces as compressive forces. And we may do one simple experiment to find the amount of extension or compression in the lab. But probably So we are not going to be able to do that. Just you should be familiar with the kind of experiment we may do in the school. So it's going to be something like this. We can put a mass at the end of a wire, and by increasing the amount of wire, we can just easily find the amount of extension depends on the masses, depends on the weight. So it's going to be a simple experiment. And after this experiment, so we may be able to draw a graph, the graph of tension against extension. So in this graph, the graph shows two regions. The first one is straight line with the F is smaller than 4 Newton. If you look at the graph, till 4 Newton, we said the y-axis is going to show tension. That means force in Newton. And x-axis is going to show extension, the amount of extension. If you look at the graph, till 4 Newton, we have a straight line. So the straight line with the F is smaller than 4 Newton. But after 4 Newton, we will have a curved line. So these two regions are going to be very important for springs. So let's continue with the properties of these forces and springs. And we said we will have an elastic limit at the beginning of 4 Newton here. Here is going to be elastic limit. Elastic limit shows the end of proportionality, where below this limit, the wire will act elastically. So between 0 and 4 Newton, the wire is behaving elastically. So that means we have elastic deformation. So between 0 and 4 Newton. So that means if you remove the force after some time, the spring or material will go back to its original state. And we have just seen in previous slides that these kind of deformations are called elastic deformation. So if the force is smaller than 4 Newton, it's going to be elastic. And above this limit, the wire acts plastically and the deformation is permanent. So if we keep increasing the force applied on the material, so that means when the force is greater than 4 Newton, so we will have plastic deformation. That means even if you remove the force, the material cannot go back to its original state. So that means it will be longer than before. We will have some plastic deformation. And as the masses are removed, wire fails to return to original length if the elastic limit has been exceeded. So if we move beyond the elastic limit and remove the forces, the material are not going to be able to return to its original length, original position. It will be longer than before. Okay, let's continue. Yeah, these graphs will be really important. The force extension graph. And we call this kind of graphs as fx graph. Fx graph. If we call y plane as F, force, and x plane is going to be as x, extension. These graphs are called as Fx force. So when we plot graphs, the independent variable goes on the x-axis. So the extension is going to be on the x-axis. If we look at the area under this curve, we see that it's equal to force times distance. And we know that force times distance is equal to what? Work. And it's going to be the work done in extending the wire. So it's very important. So the area under the line, let's write it down. The area under the line in Fx graphs gives us work done in extending the wire. Extending the wire. Okay, we should be familiar with this kind of graphs. If we are given Fx graph, the force extension graph, the area under the line in Fx graph is going to give us work done. Okay, so we will have examples about this one. Don't worry about it for now. Let's continue. Now, the next one is, what is the relationship between the force and extension? So we have an equation for this relationship, and it's a special name, special rule for this relationship. So let's see what is that. Oops, sorry. And the name of the rule for the relationship between the force and extension is called as Hooke's law. It's an important law. And the Hooke's law states that the extension of an elastic body is proportional to the force which causes it. So we saw this in our wire example before the elastic limit was reached. So if we are not moving beyond the elastic limit, this proportionality will be valid. So that means the force and extension are directly proportional if we are not moving beyond the elastic limit. So with elastic extension, the force is proportional to extension, and the Hooke's law states that the F is equal to K times X. And let's define these symbols. The F is going to be the force, always in Newton. X is going to be the amount of extension or compression. It could be both of them. The amount of extension or compression. Amount of extension or compression. And the unit of this extension or compression will be in meter. And we call the K as the spring constant. Spring constant. And from the equation, we can easily see that the unit of spring constant is going to be what? In Newton per meter. So we can understand that, we can understand by looking at the spring constant. If we have the larger spring constant value, that means that material is going to be more stiff. It will be difficult to stretch or compress that material. But when we have the smaller values of spring constant, that means the material is going to be soft. We can easily stretch or compress that material. So the K, the spring constant, is going to tell us how stiff or how soft the material is. Okay, so we said the F is equal to K times X, and it's called Hooke's law, where F is the force producing the extension or compression, X is the extension, and K is the force constant, or generally we call spring constant. And we already said that the unit of spring constant is going to be in Newton per meter. And also tells us the stiffness of the spring. And very important part, very important point for Hooke's law, this equation only applies to elastic deformations. So when we have plastic deformation, we couldn't apply this equation. We could apply this equation only for elastic deformations. It's very important part. Okay, the force constant or spring constant K. The spring constant K can be used to describe the stiffness of a spring, or can be found from the gradient of a force extension graph. So when we are given any Fx graph, fx graph, the gradient of fx graph is going to give us spring constant. For example, we can describe these two springs. If we look at spring A, the gradient of spring A, like this, it's going to be the gradient. And the gradient of spring B, like this. We can clearly see that the spring A has greater gradient. So that means the spring constant of spring A will be greater than the spring constant of spring B. So we can write like this: Ka is greater than Kb. Why? Because the spring A has greater gradient. It's the graph or the line is more steeper than spring B. So that means to extend or compress the spring A and spring B to the same amount, we have to apply more force to spring A than to spring B, because the spring A is more stiff, stiffer than spring B. Okay, continue. The other uses of Hooke's law: F is equal to K times X is not just used to describe the extension of springs, can be used to describe compressions as well as extensions. So we said that the F is equal to K times X. The X could be extension or compression. In both situations, we can use the same Hooke's law if the deformation is elastic. But if the deformation is plastic, we cannot apply Hooke's law to any question. So we said we can use compressions as well as extensions. The atom behavior in solids, wires, girders under tension or compression, anything which can be squashed, extended elastically. So we can use Hooke's law to these kind of situations. Okay, now we have one example related to Hooke's law. Let's do the question. Let's do the example. Yeah. Two springs, each with a spring constant 20 Newton per meter, are connected in series. Draw a diagram of the two springs in series and determine the total extension if a mass with 2 Newton is hung on a combined spring. So it's a little bit different question because we have two springs connected in series. So first we need to draw that one. Let's draw. Okay, we should have two springs. The first one is like this. And the second one connected in series. That means connected in like this. So let's call the spring constant of first one as K1 and the spring constant of second one as K2. Yeah, we have connected them in series like this. And both of them has a spring constant of 20 Newton per meter. K1 is equal to 20 Newton per meter. K2 is also same, 20 Newton per meter. And the question is saying that if we put 2 Newton force, 2 Newton mass at the end of these two springs, like this, it's 2 Newton. And the question is, we should find the total extension of the springs. How many centimeter or meter they will extend from their original position. Let's call this position as original position here. And from that point, how many centimeter or meter it will goes down. We should find that amount, which is basically X. So when we have only one spring, we can easily apply Hooke's law. But when we have more than one spring connected in series or parallel, so first we have to find equivalent spring constant. And there's a rule for that one. If the springs are connected in series, the equivalent spring constant, K equivalent, will be equal to, so let me write it like this first. Springs in series. And we have a special equation for that one. Equivalent spring constant equation will be like this. 1 over K equivalent is going to be equal to 1 over K1 plus 1 over K2. So we will use this equation for springs in series. So let's put in, let's calculate the equivalent spring constant by using this equation. So 1 over K equivalent will be equal to 1 over K1. K1 is given as 20 plus second one, 1 over K2. K2 is also 20. So from here, 1 over K equivalent will be equal to 1 plus 1, 2. 2 divided by 20. To get K equivalent, I'm going to turn upside down both sides. So 1 over K equivalent, if I turn upside down, it's going to be what? It's going to be K equivalent. K equivalent will be equal to, I'll do the same thing for second, the right side of the equation. I'll turn upside down 2 over 20. It will be 20 over 2, which is equal to 10 Newton per meter. So I have calculated equivalent spring constant as 10 Newton per meter. Now I can easily now apply Hooke's law. And we know that Hooke's law states that F is equal to K times X. Everything is given, just I'll put them in place. F, the weight of the mass, is given as 2 Newton. 2 is equal to the equivalent spring constant. I have just calculated as 10 times X. So from here, the X is going to be equal to 2 over 10, which is equal to 0.2 meter. So the extension of the springs will be 0.2 meter. Or if you change into the centimeter, it will be 20 centimeter. So we have done the question. It's really important to know that equivalent spring constant when the springs are connected in series or connected in parallel. So I'm going to also give you the equation for springs in parallel. So let's write it down. It's very important. Springs in parallel. So how is it going to be parallel? The parallel is going to be something like this. See, it's going to be parallel connection. So when we have springs in parallel, and let's say the spring constant of first one is K1, and the spring constant of second one is K2. So the equivalent spring constant in parallel will be equal to K1 plus K2. We just basically add them up in parallel. But in series, I have to use this equation. 1 over K equivalent is equal to 1 over K1 plus 1 over K2. These are the equations for springs in series and springs in parallel. We have to keep in our mind and learn these equations. We should memorize these equations. I'm not sure if they are given in data booklet or not, but I'll check it later and let you know. Okay, let's continue. Yeah, we have another question related to springs and Hooke's law. And what we are given again a force extension graph, Fx graph. And question 8, the state what is represented by the gradient of the graph. Okay, if you find the gradient of the graph, it's going to give us what? That is the question. First question. So we have seen that when we have Fx graph, the gradient is going to be always equal to what? The spring constant. Spring constant, which is basically K. It's going to tell us the stiffness of the spring, how stiff, how hard or how soft the spring is. The second one, we have done the AI, and the second question, A to I, this one. State what is represented by the area under the graph. So this area is going to be equal to what? So we know that if you multiply force times distance, it's going to be work. Or, and we also know that work is equal to what? The energy stored in a spring. So the area under the graph is going to be work or energy. Energy stored in a spring. Energy stored in a spring. Yep. So these are the answer for the second question. We have also done this one. Now let's do now question B. The spring constant, the spring has a force constant or spring constant, which is equal to 80 Newton per meter. The spring is compressed by 0.06 meter within the limit of proportionality and placed between two trolleys that run on a friction-free horizontal track. Each trolley has a mass of 0.4 kilogram. When the spring is released, the trolleys fly apart with equal speeds, but in opposite directions. And question I, how much energy is stored in the spring when it's compressed by 0.06 meter? That is a question. Actually, we haven't seen that equation, but it will be on coming slides, but we can write it down now. So when we have springs, the energy stored in a spring, there's an equation for that one. The energy stored in a spring is equal to 1/2 times K times X square. That one is going to be the equation. Or we can also get this equation by using the graph. How? Because we said this area under the line is going to be equal to what? Work or energy. So what is this area? It's basically the area of triangle. So if I calculate the area of this triangle, it's going to be what? I know that the area of the triangle, the equation is equal to 1/2 times this side, which is equal to force F, times base, which is equal to X. I also know that from the Hooke's law, the F is equal to what? Kx. If I put Kx instead of F, the equation, the area is going to be equal to 1/2 times K times X, which is basically equal to 1/2 times K times X squared. So the energy stored in a spring is equal to 1/2 times K times X squared. Now, by using this equation, now I'm going to calculate the energy, question I. So let's calculate. So energy is equal to 1/2 times K. K is given in the question, 80 Newton per meter. 80 times the extension square, which is also given as 0.06. 0.06 square. So if we calculate this one, so let's calculate 0.06 times 0.06 equal to this one, 0.0036 times 80 divided by 2, which is equal to 0.144. The energy stored in the spring will be equal to 0.144 joule will be. So we have calculated energy. Okay, next question. Let's do the next one. Next one is this. Explain why the two trolleys must fly apart with equal speeds. Okay, so let's read the question again. The spring is compressed by 0.06 meter within the limit of proportionality and placed between two trolleys. Okay, let's assume we have two trolleys like this, and we have spring between them. We compress them. So when we release, they will move in opposite direction. And the question is asking, why the two trolleys must fly apart with equal speeds. Equal speeds in opposite directions. Why? That is a question. And the answer for that one, the law of conservation of momentum must be obeyed. So the momentum of each trolley must be equal but opposite and as momentum. So the masses are equal. So that means the speeds must be equal because they have the same, both of them have the same mass, m. To conserve the momentum, conservation of momentum, they must have equal and opposite speeds. Actually, we can also write the equation for this one, the conservation of momentum. What was the conservation of momentum? The conservation of momentum states that the total momentum before releasing the spring, total momentum before releasing spring must be equal to total momentum after, so when we release the spring. So we know that before release the spring, the trolleys are not moving, so that means total momentum is 0. And when we release the spring, the total momentum after releasing must be also 0. So how we should have this one? So m1 times v1 plus m2 times v2. From here, if we choose the right side, let's call this one as m2, this one is m1. If we choose right side as positive, the left side is going to be negative. And from here, 0 is equal to m1. Both of them have the same mass. Let's say just m times v1. v1 is to the left side, minus, let's put minus here, minus v1, plus m times v2 is to the right side, positive, just v2. If you take negative to the right side, it will be like this. M times v1 is equal to m times v2. Now cancel m. What is left? v1 must be equal to v2. So we have proved this one. Explain why the two trolleys must fly apart with the equal speeds. Yeah. According to the conservation of momentum, they must have the equal and opposite speeds to conserve the momentum before and after. Yeah, that's all. We have done that one also. Now we will do the last question. Let me clean everything, then do the last question. And what is the last question? Last question is calculate the speed of each trolley. So how can we calculate the speed of each trolley? So we know that the work is equal to the change in kinetic energy, right? So that means the total energy we have just calculated, the total energy we have calculated from this equation, the energy is equal to 1/2 times k times x squared. And we have calculated as 0.144 joule. So that means this energy must be equal to the total kinetic energy of trolleys. So I'm going to equalize like this. 0.144 must be equal to 2 times, because we have two trolleys, kinetic energies, 1/2 times mass times velocity square. Now everything is, you can just put them in place. 0.144 must be equal to 2 canceled by 2. It's going to be what? What's left? M. M is given. Each trolley has a mass of 0.4 kilogram. 0.4 times velocity square. From here, velocity square will be equal to 0.144 divided by 0.4, which is equal to, let's divide, 0.144 divided by 0.4 is equal to 0.36. 0.36. So v squared is equal to 0.36, and v will be equal to what? V will be equal to in square root 0.36, which is equal to 0.6 meter per second. So we have also calculated the speed of trolleys. The energy stored in the spring must be shared between the trolleys as kinetic energy. So that's why we have written 2 times the kinetic energy of each trolley. And the speed of trolley must be 0.6 meter per second. The one is to the left side and one is to the right side. Yep, I hope everything is clear. So let's continue. Now we'll continue to the springs. Now we will have some more definitions related to springs. The second part is the mechanical properties of matter. So let's continue. So what happens to work done on a spring? Work done to stretch a spring. So when we do any work, so it's going to be a stretch or compress. So we can make extension or compression because of this work done to the spring. So we know that work done is equal to F times T. However, since the force required to stretch the spring is not constant, F gradually increases with extension. And just we mentioned that if we are given force time graph, the area under the line in Fx graph is going to give us work done. And we said that this area is going to be the area of triangle. And we know that area of triangle is equal to 1/2 times height times base, and which is going to be basically equal to F times X divided by 2. And if we place Hooke's law in this equation, we know that F is equal to K times X. Since F is equal to K times X, the equation can also be written as the work is going to be equal to K times X squared divided by 2. Or basically, we can write work or energy stored in a spring is going to be equal to 1/2 times K times X squared. That equation is also similar to kinetic energy. So what was the kinetic energy? Kinetic energy is equal to 1/2 times mass times velocity square. So we have, in both equations, we have 1/2s. In kinetic energy, we have mass as a constant, and we have spring constant in springs, and velocity square, extension or compression square. These equations are a little bit similar. So we can easily keep in our mind these equations if we write them in this way. Okay, let's continue. Elastic potential energy. Since work has been done on a spring, to stretch it, the energy is stored as elastic potential energy in the spring. Many toys, clocks, use springs to store energy, which is released as the item is used. And this energy, elastic potential energy of work, is equal to 1/2 times K times X squared. And we can use this equation in compressions or extensions. In both of them, we may use them. It doesn't matter. It's going to be compression or extension. And E in this equation is going to be energy. And we know that unit of energy is going to be always in joule. And the K is going to be spring constant. And we know that unit of spring constant is going to be Newton per meter. And finally, X is going to be extension or compression. Extension or compression. And the unit of extension or compression is going to be in meter. And that should be square. Yeah. Next one. So what would happen to extension if we remove the masses now? Okay, let's assume we put some masses to the spring and we extend the spring till some point. And at that point, if we remove the mass, what will happen? So since we have passed the elastic limit, so if we pass the elastic limit, the wire will not go back to its original length. However, it will reduce its length a bit. The area under this line represents the energy released by the wire. So we just move beyond the elastic limit, and it goes like this. At that point, when we just remove the mass, so the wire or material are not going to be able to go back or return to its original position. It will go back to here, okay? Because this is going to be a kind of plastic deformation because we applied too much force and we moved beyond the elastic limit. That's why. So what happens to the rest of the energy? So we have added energy to the wire to extend it. The sum of this energy is released from the wire as it relaxes, and the rest of the energy causes wire to become heated. Yeah, the sum energy will be used for stretching, and the sum energy will change or will be wasted as heat energy. So the area under the line, again, is going to give us the first area, the heat input energy, and the second area is going to be output energy. Actually, we are not going to see very complex questions related to Hooke's law. We will have generally straight lines, the force extension graphs. Okay, now loading and unloading. Now we have some different descriptions. We will go over these descriptions now. So again, we have the force and extension graph, Fx graph, basically. The different materials respond differently to being stretched, compressed. Yeah, of course, it depends on the material, how they're going to respond to compression or extension. This causes their force extension curves to have different shapes. Often the loading curve, now that part of the curve is called as loading because we're still applying force to the material. Often the loading curve, the FE curve, the force extension curve, as the force is being applied to a material, is different from the unloading curve. The second part of the graph is called as unloading. Why? The FE, force extension curve, as the force is released from a material. So at this point, we just remove the force. The force removed. Okay, so that's why it goes back to some point, but it couldn't go back to the original position because this is the plastic deformation. We already exceed the elastic limit. Here is the elastic limit. If you exceed the elastic limit, so it's going to be plastic deformation. Till here, it's elastic deformation, But after that point, it's plastic deformation. Yeah, the shape of loading and unloading curves can help us identify a material. Now we will see different shapes for different materials. So let's see. What type of material could these be showing? Describe each graph in detail. Now we have 3 different graphs. And the first one is going to be metal wire spring. The second one is going to be a rubber band. And the last one is going to be polythene bag. So let's see what happened. They could either be the polythene bag, metal spring, and rubber band. Detailed descriptions. So what we will check for graphs, what we will look at on the graphs. The first one is Hooke's law obeyed? The second one is is the extension elastic or plastic? And the last one is, what happens during unloading? So we have to ask these three questions when we are looking at any graph. Now we will check one by one. Now, first one, we will start from the first one. The first one is metal wire spring graph. If we have any metal, any spring, the graph, Fx graph, is going to be always in this shape. So the loading follows Hooke's law until the elastic limit is reached. See, here's the elastic limit, and we have a straight line. So that means the Hooke's law is obeyed. Below this limit, if you just move beyond this limit, unloading will follow the loading line. See, if you move beyond the elastic limit and remove the force, here is force is removed, force removed. What happens? Unloading will follow the loading line. It goes back to some point. And it's very similar to the loading graph, loading line. Above the limit, unloading is parallel, but offset from loading due to permanent plastic extension. Because we already exceed the elastic limit, we had some plastic deformation. That's why when we remove the force, the material couldn't go back to its original position, 0. And the last part, after unloading, the material is longer than it was originally. It has suffered plastic deformation. Yeah, because of the plastic deformation, it's going to be longer than before. For example, let's assume before applying the force, let's say the length of material is 10 centimeter, let's assume. But when we apply force and go beyond the elastic limit, remove the force, it couldn't go back to the 10 centimeter. It must be longer than 10 centimeter. Probably it will be, let's say, 11 centimeter. Okay, it will be longer. So this graph belongs to metal wire or springs. When we have any metal wire or springs, the graph is going to look like this. And we should be familiar with these properties. The second graph. The second graph is going to be rubber band. It's a very different graph. Let's see the properties of this graph. The loading doesn't obey Hooke's law. As you see, we do not have any straight line for loading. It doesn't obey the Hooke's law. Deformation is elastic, but loading and unloading curves are different. Yeah, we have loading curve. The loading means when the force is applied, and unloading means when the force is removed. More work is done stretching the rubber than is done when it's released. This extra work is released as thermal energy. And as we said, we can easily understand the amount of work done on loading and the amount of work done on unloading. How? We said the area under the line in Fx graph is going to give us what? Work or energy. So for loading, we will have that amount of energy we will have for loading. But for unloading, the unloading is going to be here, which is clearly smaller than loading. So the work or energy loading greater than the work or energy unloading. Yep. And the next one, the more work is done stretching the rubber than is done when it's released. This extra work is released as thermal energy. We just said it. And finally, the loop shape to the two curves is called as a hysteresis loop. Hysteresis loop, the name of this curve. this curve is going to be as hysteresis loop. It's for what? It's for rubber band. And the last one, polythene bag. The loading again doesn't obey the Hooke's law. We do not have a straight line. For Hooke's law, we need a straight line that the force applied must be proportional to extension. But in here again, it is not proportional. The suffers plastic deformation with even a small force. Yeah, well, even when we apply a small amount of force, we will have plastic deformation. That means after removing the force, the material couldn't go back to its original position. Yeah, that's the graph for the polythene bag. So all this stress is causing me a real strain. What does this mean? Now we have new definitions in springs, in materials: stress, and strain. These have different meanings in physics. So let's see what they are. Strain versus stress. These words are used every day, but in physics, they mean something specific. Now, first look at stress. The symbol of stress is going to be like this. And the meaning of stress: a force per unit cross-sectional area applied to a solid object. So that means stress is equal to the force per unit cross-sectional area. So that means F divided by A, cross-sectional area. The units are Newton per meter square. Here we can easily find the unit as Newton per meter square. We know that the unit of force is Newton, and the unit of cross-sectional area is meter square, and the unit of stress is going to be what? Newton per meter square. Same as pressure, but pressure applies to liquids, gases, also called Pascal. But we are not going to use Pascal here. We will use Newton per meter square generally, but sometimes it could be used as Pascal. So it's a definition of stress: the force per a force per unit cross-sectional area, F divided by A. It's very similar to pressure equation. Now, the next one is strain. And the symbol for strain is going to be like this. The strain means extension per unit length of a solid object. Extension per unit length. So that means strain is equal to extension, X, per unit length, divided by the length of the material, X over L. Strain is a unitless. Why? Because the extension is going to be in meter, the length is going to be in meter, cancel each other, and there's no unit. No unit for strain. No unit. Strain is often quoted as a percentage. So for example, 0.03 means is going to be 3%. The object has extended by 3 centimeters for every meter of original length. So these definitions are a little bit confusing. We just need to repeat them, revise them, and we will be able to remember them easily. Stress and strain. Stress means the force per unit cross-sectional area, and the strain means extension per unit length, F over A and X over L. Okay, the stress causes strain. Stress causes strain. We said stress is equal to force per cross-sectional area, and strain means extension per unit length. So that means when we apply any force, any stress, so it will cause extension. That means strain. How much strain is caused depends on the stiffness of the object. With a stiff material like iron, a large stress will only produce a small strain. But with a soft material like rubber, a small stress is enough to produce a large strain. And the final definition for this chapter, the Young modulus. The ratio between stress and strain in a material within the limit of proportionality is called as Young modulus. And we will show the Young modulus by Y. And the Young modulus is equal to stress divided by strain. And we can also write like this. The Y model is equal to what was stress? The stress was force per cross-sectional area divided by strain is what? The extension per unit length. And if we do like this, the Y is equal to F over A times, if I turn upside down the second one, it will be what? L over X. And we can write the Young model as, the Young model is going to be equal to F times L divided by A times X. We can use this equation or this one. Both of them could be used in questions. Stress divided by strain is going to be equal to Young modulus. It's a kind of ratio. Yeah, we said we can write the Young model as force times length divided by area times extension. It's called as Young modulus. Yeah, so we have finished all topics in this chapter, the materials. Now we may do some more questions and make it clear. So let's read the question. The first question is, this is the force extension graph for a metal wire of length 2 meters and cross-sectional area 1.5 times 10 to the power minus 7 meters square. So the first, let's write given values. It will help us to see what kind of equations must be used. So given values, givens. So what is given? Metal wire of a length 2 meters. Length is given. L is equal to 2 meters. What else given? Cross-sectional area is given. Cross-sectional area, which is equal to 1.5 times 10 to the power minus 7 meters squared. This one's given. We are also given fx graph. And question A, calculate the Young modulus. Okay, we should calculate the Young modulus. We have just seen that Young modulus is equal to F times L divided by A times X. Okay, so we know A given, we know L given, and we will get F and X from the graph. If we use the last point on the graph, that point, the X is going to be this one, 0.8, and F is going to be this one, 10. So let's use these values. Young model Y is going to be equal to F. F is going to be 10 Newton, 10 times length given as 2 meters divided by cross-sectional area, 1.5 times 10 to the power minus 7 times extension X, 0.8 millimeter. But I have to change into meter. So 0.8 times 10 to the power minus 3. So from here, Young model is going to be equal to 10 to the power minus 3, 10 to the power minus 7. It will be 10 to the power minus 10. If we take it upside, it will be positive 10. 10 to the power of 10 times 10 times 2 will be 20. 1.5 times 0.8. Let's multiply. 1.5 times 0.8 equals 1.2. 1.2. So 20 divided by 1.2. 20 divided by 1.2 equals 16.6. 16.6 times 10 to the power of 10. So we have calculated the Young modulus. So what about the unit of Young module? So we can easily get the unit of Young module from the equation. So we said Y, the Young module is equal to F times L divided by 8 times x. If I write the units in place, the unit of force, Newton, times the unit of length, meter, divided by the unit of cross-sectional area, meter square, times the unit of extension, meter. Cancel meter. And the unit of Young model is going to be same as the unit of stress, Newton per meter square. Same unit it will have. So we have done question A. Now we will do question B. Determine the energy stored in the wire when the extension is 0.8 meter second. 0.8 millimeter, sorry. Determine the energy stored in a wire when the extension is 0.8 millimeter. So I'll clean that part. Okay, we can find the energy stored in the spring by using the equation. The energy is equal to 1/2 times K times X squared. I can use this equation, or because of the spring constant is not given in the question, I can also use the area under the line in Fx graph is going to give us work or energy. So I'll calculate the area of this triangle. So the area of this triangle will be equal to what? 1/2 times height, given as 10, times base, 0.8, 0.8. So the force is given in Newton. The extension is given in 0.8, but we should change into the meter. So 0.8 times 10 to the power minus 3. From here it will what? 10 simplify by 2, it will be 5. 5 times 0.8, it will be 4. So 4 times 10 to the power minus 3 joule. So the amount of energy stored in the wire will be 4 times 10 to the power of minus 3 joule. And the last question, C, calculate the work done in stretching the wire between 0.4 and 0.8 millimeter. Calculate the work done in stretching the wire between 0.4 and 0.8 millimeter. Before doing that question, we can also solve question B by using this equation. E is equal to 1/2 times K times X squared. And I can easily get X by using the gradient. We know that the gradient in Fx graph is going to give us what? Spring constant. So the gradient or spring constant is equal to 10 divided by 0.8 times 10 to the power minus 3. From here, 10 to the power of 3, if it goes to upside, it will be plus 3. 10 times 10 to the power of 3 divided by 0.8. So 10 divided by 0.8, 10 divided by 0.8 equals 12.5. 12.5 times 10 to the power of 3 Newton per meter. So it's K. Yeah, then now I can put in an equation. The energy is equal to 1/2 times K, 12.5 times 10 to the power of 3 times X squared. What is X? 0.8 times 10 to the power of 3 square. It will be 0.64 times 10 to the power of minus 6. So from here, 12.5 times 0.64 divided by 2 will be, again, same answer. We will have 4 times 10 to the power minus 3 joule. See, we have received the same answer. So we can calculate the energy by using the graph. The area under the line is going to give us energy, or by using the equation 1/2 times K times X squared, and we can get K by using the Fx graph. And the gradient in Fx graph is going to give us spring constant. And the last question, we may do the last question also by using the area under the line. And the question is asking the work in stretching the wire between 0.4 and 0.8. So we should calculate this area. 0.4 is here, 0.8 is here. So we should just calculate this area. And we can calculate this area by separating the area into the two parts, the area of rectangle and area of triangle. So that part is going to be, let's say here is almost 5. So 5 times 0.4. And this area is going to be again 5 times 0.4 divided by 2. It will be like this: 5 times 0.4 plus 5 times 0.4 divided by 2. So which is equal to 2 plus 1, which is equal to 3 times 10th power of minus 3 joule. Why? Because these units are given in millimeter. At the end, we should change millimeter into the meter. So it will be 10th power of minus 3. And the final answer is going to be 3 times 10th power of minus 3 joules. So we have done also last question. So these are the questions related to today's topic. And it's enough for today. So the next lesson, we may do some more questions related to materials and also related to momentum. Because as I said before, you have some mistakes in questions. So we can solve these questions again together and to make everything clear. Yeah, thank you very much. Have a great evening and see you next week.